Welcome to this talk at the MongoDB Live 2021, where I want to talk about how we at Bosch have transformed binary real data to information that can be read and understood by our engineers and analysts, and how we used MongoDB to do so. First of all, I want to move you back 130 years, and we want to look at cars at that particular time. Look at it. It's quite different from nowadays cars, right? So it has, of course, already four wheels and a steering wheel and an engine and headlamps, but it was in no way any electronic or electric component in it. And that has changed, and that has changed a lot. We're now going to a future where cars will communicate with other cars in the streets and will communicate with the infrastructure around, will communicate with traffic lights and public base stations that tell the car about happened accidents in your area, or construction sites, or road conditions and traffic density. And this all is for enabling us to, or our cars to drive autonomously, so for their own. And we are part of this movement. We built just a small little block of that. But that is where we are working on. And this has started in 2012. Bosch engineers looked at the cars they were developing components for, and they saw that the car is full of software. They actually have counted up to 100 million lines of code that actually drive a car. And this huge amount of code and a complex communication network that is part of such an IT system called car needs comprehensive testing and needs a good understanding of what happens in each and every component to be safe and secure and to not risk anybody's life because of software failures, because of misprogrammed functionalities. And so they looked at their processes and their way how they how they know what they actually what the components do in their car, and then they saw, oh, this is kind of a manual and error-prone process yet. So they saw you can of course connect to the components. You can plug in a cable and plug it also into your notebook, and you can download the data, but it's not sufficient to control this kind of complex system to really know what happens inside. And so they start to work on a solution, and the solution now exists, and it's Bosch IoT Insights, a service that is offered Bosch internally, but also to the world, to collect data from devices and decode that data and make it analyzable, and offer it to the engineers and the analysts to understand their device better. So my name is Steffen Gürtler. I'm working at Bosch since 2010. Had my master degree 2005, and I'm part of this software solution since 4 years. I want to bring you here information how complex it actually is to understand the vehicle, how MongoDB has helped us to make the data accessible and to store and analyze it, and finally how you can have your own trial. So the Bosch engineers looked at the car and they saw two main interfaces to the data. The first one is cars have a diagnosis interface. So you can already connect the cable to it and read out certain diagnosis statistics and information from the different parts of a car. But this is meant to be used when the car is stopped, when it's off, when it's at the workshop for being repaired or maintained or something. And that's not meant for doing it during when a car is moving. So the other option they found was to actually look at the communication that is done internally, because there are 70 up to 120 different components, electronic control units in a car, and they all exchange information, data, signals. And so they thought about, can we make use of that? And actually, all the data in vehicles flow there, not in JSON or XML or something like this kind of encoding standards that humans already can automatically read. No, they are actually transferred in a very short time frame and in a very short and raw encoded way, because car electronic is made for rough environments. You have to think about it. A car is not only on driving on flat streets. No, it is used even on rugged streets or even off-road, and it's used in very different areas of the world. Maybe a desert, maybe the Arctic. There are a lot of scenarios a car has to stand, and this is also the reason why the control units and their networking is kind of limited to certain processors, to two-wire connections, and to fulfill a level of security and safety that is, for example, normally not the case for consumer electronics or for even office equipment. Then to decode such binary strings, humans cannot read that. But the development process of control units already designs the messages and the signals inside the messages that are transmitted, and this is typically done in the automotive industry. In many cases, it's done with DBC files. That actually comes from a proprietary tool, but it's nowadays used in many different process chains and tools, so it's no longer so proprietary, and it's actually something that is very common. So we were able to use the information that is inside DBC files to understand the binary data. Some background how car information, the car communication is actually working. We have here an example made with the cruise control ECU. Cruise control ECU is having two kinds of input itself. So it on the one hand has some sensors that measure physical values, and it has also set points that the driver gives. For example, he sets the required velocity, and then the cruise control functionality uses information to actuate. It means that it controls different parts of the car, either via controlling small motors or valves, or it sends signals to other ECUs to trigger a specific action. And to be able to do so, it's connected to the driver CAN. And CAN stands for Controller Area Network, so it's made especially for this environment inside a car, and for this kind of hardware, small little control units. And it's a bus system, so that means that when one ECU is sending something out on that bus, all the other ECUs on that bus can receive this message and can react on that. So as I've told, there are more than just 4 or 5 ECUs in a car. There are typically 70 to 120, and so you don't have just one such a network in a car. No, there are multiple ones, 4, 5, 6, depending on the car, and they are connected typically over one central gateway, so that gateway can forward specific signals to the other bus systems. And this is an important part of the design process in the car manufacturer that has to do. And for example, he has to make sure that the message to trigger the airbag has a very high importance level, so it is really sent to the different networks in case of if a crash is detected. Yeah, it's not blocked by we choose the window up and down signal or something like that. And 70 up to 120 ECUs, that means there are a lot of information that are exchanged over these buses. And this also means you can learn a lot from these messages. So we now connect a communication unit to this bus system, and the communication unit can now also receive all these signals, store them internally, and then every 2 or 3 seconds send them out to our service. And that's how this looks like then. This is the result and tracing file over several seconds of such an internal network. And as you can see, it's not readable for humans. It's many different columns and a lot of hex numbers in there, but it's not made for further analysis, further understanding from humans. And yeah, now I want to show you how you can actually understand these messages better. I've prepared a CAN DBC file. I used a free tool from Vector Informatics to do so. As mentioned, there are many tools out there. I just have picked a random one and recreated the network from the slide. So I have an ACC, an engine, an ESP and gateway and gearbox added to it, and I've just added one message to the gearbox that it sends out, and then I can design this gearbox message, just assigning each and every bit to a signal. So I can even have signals that are just 1 bit long, and again, the reason is that we are in a car network that is made to transfer very small amount of data at a certain bandwidth. By the way, in cars we have a bandwidth of roughly 200 to 500 kilobits. And as you can see here, in such a scenario, you need to use every and each bit. So that is why many of the signals do not use a full byte, but just 4 bit or 1 bit. Here the temperature, for example, uses 12 bit, which is kind of uncommon in the IT industry, but for automotive electronics this is very important. And if we now look at this particular signal, which is 12 bits long, I can transfer temperatures from minus 60 degrees Celsius up to 76 degrees Celsius. Again, cars drive in Arctic zones also, and in deserts, like they do in deserts. And to press this in 12 bits, I have to specify a certain factor, also how many, or what is the resolution of my signal, how many separations of measured temperatures I can do, and certain offsets, so they move it to a certain physical value range, -60 plus 76. And here you see also that one major function of this DBC file is to say, technically I have 12 bits where I can send over an integer value, but physically this means a certain temperature. So we have a conversion between a technical value and a physical value. And this kind of information we can now use at Bosch IoT Insights. So this is a typical start page if you have subscribed to Bosch IoT Insights plan. You see some project stats, and you will find the decoding under services decoder, and here you can upload such a DBC file. As you can see here, there are more formats we're supporting, most of them from the automotive industry, but for example we also support Google protocol buffers, and that is used for example in smart metering projects. So I select the DBC file I've shown. I will give it another name because there's already one uploaded. So when I now upload that one, I can copy over such an binary value like this one, copy, insert that here, say what message number was that, and then looking at it, we have here the gear state. Operation temperature, for example, and in that case somewhere in this byte field there was decoded that there was measured a value of 26.7 Celsius. The next question was, how can we get away from any manual work here? And we've designed a data processing pipeline that allows the cars to send the data to our cloud service, and we are automatically decoding the information out of it and store this in the MongoDB collection. Here you can see the service on the one hand that receives the data is called the data recorder. It just opens up an HTTP interface where the data is pushed to, and we then store this to as it is, raw as it is, just the whole content of the HTTP call in a collection called input data, and we use here the feature from MongoDB to be able to just store byte arrays. And then we have this processing pipeline apps that actually listen for such incoming data. And here we have the next MongoDB feature, the change streams, that automatically inform us that, or inform the pipeline apps that there is new data, and then the data is already in memory by the change stream, and we can hand this over to the DBC parser, which loads the decoder file, also from a MongoDB collection where all these files were just stored into, again, as a byte array, combine those two information and creates a MongoDB document that the output step can store into the collection processed data. And the processed data is then the source for all the further steps like querying, aggregation queries, lookup queries, and you can add indices, and you can use all the MongoDB features there to analyze the data. One important aspect in the design of Bosch IoT Insights was also that we want to allow thousands of cars to upload their data. We have many customers that already have hundreds of cars, and we are currently since half a year have a customer that has already thousands of cars. So we have prepared for this last year, and we made Bosch IoT Insights horizontal scalable, and that actually means that our processing pipeline apps is a Docker image that runs multiple times in a container service, and just listens for all these instances, listen for incoming instances, and here we use another MongoDB feature that's just the atomic answer. So the first watcher that is able to create and document in a collection called processing status is the one then responsible for passing the binary bytes into a MongoDB document, and all others will also try but will fail because the document with that ID already exists. And what we were also made possible is that our customers can actually upload own bundles of code. We store them in a gridfs collection in MongoDB, and that made it possible for them to enrich the data even further. For example, they add weather condition or street condition from external services. I also want to show you that part in processing pipelines. We have a DBC decoding pipeline example prepared, and here in configuration you see the 3 steps: the input trigger, the parser step, and the output step, as I have mentioned it in the slides. And here we see the DBC file again. We see a regular expression that tries to extract from these can trace files the important information blocks like the timestamp, the can ID, and the actual message. And when you now upload such can trace files, it is processed in this pipeline. You see that here also the processing log, and finally when it's done, we can have a look at the data in the data browser, where we find this particular document here in decoded. So here in payload we see the decoded messages again, and we will have again the gear state message made readable for humans, and further analyzing, made it possible to further analyzing it with MongoDB. What we then have learned is that this one-to-one storage in MongoDB is good for the start. So even new projects often start like this, and we make use of another important MongoDB feature here, that is MongoDB does not enforce any schema. It's schema-less, and so they can have substructures in their signals, whatever they like, and MongoDB just is able to still work with this data, and to accept this data, and allows them to make further information, add further information into. But for achieving a certain kind of performance, you have to change the format a bit and make it more analyze friendly. So we have changed from the one-to-one relation, from one message in a canvas to a document in MongoDB, to a document that collects several of such messages into just one MongoDB document for a particular vehicle. And for these projects with thousands of cars, we have changed that even further to store a document per signal, per time frame, per vehicle. We are currently working on a new concept because MongoDB's time series feature is out. So we were part of the beta program. We already tried it a bit, and we're now hoping for a new maturity level that uses time series to store this information from the cars. Last but not least, you can try all this on your own. In a service catalog on BoschIoTSuite.com, you'll find this service. It's called Bosch IoT Insights. Here we explain a bit about the background and a bit about the the internals. And we give you an overview about the different service plans you can book and a pricing calculator, so you can estimate what it would cost you in your specific scenario, and can compare it, for example, what it would cost you if you did this all on your own. And we are also on the AWS marketplace, so you can search there for Bosch IoT Insights and you will find the same information and the same service plans there. So, thank you for listening. If you have any questions about decoding and analyzing or any of the MongoDB features we have used, don't hesitate to use the following session to do so. I'm done with the presentation here, and I wish you happy decoding.